Computers use different levels of memory because each type has different speed, size, and cost. At the top are registers, which are very fast but very small and located inside the CPU. Below that is cache memory, which store frequently accessed data to reduce access time. And next is a main memory or RAM, which is larger but slower than cache. Finally, we have secondary storage such as SSD or hard disk, which are the slowest but have the largest capacity. In general, as we move down to the hierarchy, speed decreases and storage size increases.
Cache memory is so important, so let's look at the one cache design, which is direct the mapped cache. In this design, each block of main memory can only be placed in one specific cache line. This makes the cache simple and fast. For example, if memory block is already stored in mapped cache line, the CPU gets a cache feed. If that block is replaced by another block, accessing it again will cause a cache miss, which slows down performance. This shows the trade-off of simplicity versus possibly conflict.
Next, we move on to machine-level data, starting with number system. Computers mainly use binary, but we often convert between binary, decimal, and hexadecimal. For example, binary 1011 is equal to decimal 11 and decimal 29 is equal to hexadecimal 1A. Hexadecimal is useful because it represents binary values in shorter and easier form.
For integers, computers use two complementary representation. This method allows both positive and negative numbers to be stored efficiently. In a 4-bit system, the largest positive value is 0111, which is plus 7. Adding 1 to a result in 1000, which represents negative 8. This is known as overflow, where the value exceeds the representable range.
Computers also use floating point representation based on the IEEE 754 standard. A floating point number consists of a sign bit, an exponent, and a fraction or mantissa. This format allows computers to represent very large or very small numbers with reasonable precision.
Data representation affect performance and memory usage. Integers are use less memory and are faster to process, while floating point number require more space and processing time but provide a higher precision. Choosing the right data types help improve efficiency.
Now, let's discuss parallel processing. One common processor organization is symmetric multiprocessing, or SMP, where multiple processors share the same main memory and have equal access to resources. This allows tasks to be executed in parallel, improving performance.
There is also a difference between multiprogramming and multiprocessing. Multiprogramming use one CPU that switches between tasks, while multiprocessing use multiple CPUs that execute tasks at the same time.
Finally, we have Amdahl's law, which explains the limitation of parallel processing.
For example, if only 50% of program can be parallelized, the maximum speedup is about 2 times, regardless of how many processors be used. This shows that the serial part limits overall performance.
In conclusion, memory hierarchy improves efficiency, data representation affects speed and memory usage, and parallel processing increases performance but still has a limit.
Right. Understanding this concept helps us better understand how computer system works.